And so previously what we've looked at is we've looked at only specific heat or only latent heat calculations. Ones where we have liquid water at 10 degrees and we heat it up to 75 degrees. And so if we were doing this here, we say we got 10 degrees, we want to heat it up to 75 degrees, and so the section we're on is just this section right here. Since we're only on one section, then we have to look and say, is this a latent heat calculation or a specific heat calculation? And so we say, well, in this case, the temperature is changing. So since the temperature is changing, we're going to use the specific heat, Q equals Cm delta T. And so since we're using this, then we can simply say C for this is water right here is just 1. M is whatever your mass is right there, whatever the problem gives you. Delta T would be going, we said, from 10 to 75, so it would be 65 degrees. And so on and so forth. You can find what the heat is just like that. Those are the ones we've done so far, or ones where we say that we've got, 100 degree water and we're going to boil it all away. And so in that case, you'd say, well, this is going to be a latent heat problem. And so we use Q equals MHL, or in this case, it'll be HV because it's heat of vaporization. And you go ahead and solve that. But what would happen if we didn't have a situation like that? We had something that was a little more complex. And instead of having the temperature go from, say, 10 degrees Fahrenheit up to 75 degrees Fahrenheit, what if we went all the way to 110 degrees Fahrenheit? Then we'd have to go all the way up the liquid phase. Then we'd have to boil it off. Then we'd have to go up the steam phase. And in that case, we don't have a calculation that's able to do all three of those. You absolutely want to make sure that you don't go ahead and just use Q equals Cm delta T for the whole thing, because it has this nice long section in the middle where it's boiling off, and that takes up a lot of energy. And as well as the fact that if you use Q equals Cm delta T, do you use the C for water or do you use the C for steam? They're two different C's. For water, it's liquid water, it's 1 versus steam is 0.48. And so what you've got to do instead is that instead of setting this up do it as one calculation, you've got to break this down into 3 parts. That the first part is going to be on the first section, going from where we started at 10 degrees up to the end of the water section right up there. And for that, we're going to use a Q, but instead of being just Q, we're going to call it Q1, the heat for the first section. And in this case, because of the fact we're in a temperature change section, it's going to be Q equals Cm delta T. Now for our next section here, we're going from basically where the water and steam start, or basically where it starts changing phase from water into a gas, from liquid water into a gas, to the end of that section. And so at the end of that section, this is going to be our second heat, Q2. And that one's equal to MHL, or MHV in this case. And then we have our last section going from the beginning of the steam section at 100 to the very end of it, and that's going to be our Q3. Similarly to the original one, since the temperature changes, we'll use Cm delta T. Once we've got those 3, once we've found what Q1 is and found what Q2 is and found what Q3 is, we can find the total energy Q simply by adding them up. Q is equal to Q1 plus Q2 plus Q3. And then we add those up. That tells us the total heat that's involved here. And so keeping going here is that our next possibility is that sometimes you'll have a problem where you know the amount of calories that were added, but you don't know what the total mass is. And this is a particularly difficult issue because of the fact that you use mass in every single one of those equations. And so as a result, what you have to do is you basically, if you know the total energy that you have, so in this case we've added 7,500 calories, is that what you have to look at is you have to basically find each of your Qs, Q1, Q2, Q3, Q4, Q5, however many you have, in terms of M. So basically, if you had, Q equals Cm delta T, is you could put in C and you could put in delta T, but since you don't know M, you have to leave it as M. And so let's say you do that, and whenever you do it, is that basically Q1 is equal to 4.5 M, Q2 is 17 M, and Q3 is 113 M. Now, since you know that the total heat, Q, is equal to Q1 plus Q2 plus Q3, what you can do is you can rewrite this by substituting in all your M's. So first thing we know is we know the total heat is 7,500 in this case. So we've added 7,500 calories. And this equals Q1. Now we found Q1 was 4.5 M. And then plus our next one, which is Q2. Q2 is 17 M. And then plus our last one, which is Q3 is 113 M. 113 M. So once you've got that, you can then add up all your m's over there on the right side. And so we get that 7,500 is equal to 4.5 plus 17 plus 113. So working that out, we say 4.5 plus 17 plus 113. And so we get 134.5. So this is equal to 134.5 m. To solve for m, we simply then divide both sides by 134.5. On the right side, it cancels your 134.5. On the left side, we'd say 7,500 divided by that 134.5. And so I get 55.76. So I get a mass of 55.76 grams. Now, significant figure-wise, it looks like the thing that's got the smallest. We got 2 significant figs here, 2 sig figs here. And so based on that, we'll run this to 2. And so we get a mass of 56 grams as our final answer here. And so that's how you'd go ahead setting up a case where you don't know the mass.